started to look at matchings, and we looked at matching in insertion only streams. Okay, matching in insertion only stream. Okay, and what did we notice? That for unweighted graph, when edges are coming in the stream, we can compute a maximal matching and what does this gives us? How much space does it take? So since it's a maximal matching, it is never going to take more than order n log n space, and approximation factor is 2. Right? And then we try to generalize this algorithm to a weighted graph. Right? If I want to find just insertion only stream and matching, then edges are coming, I can maintain a maximal matching. Right? But if I have weights, I do not know how to maintain this. Right? So this is what last time we saw, an algorithm based on local search, local ratio basically. So what was in our algorithm? Our algorithm was very simple. It was based on the following simple observation, that what does local ratio tells us? The local ratio tells us that if locally I can maintain certain approximation factor, and or basically if I do a weight decomposition W in W1 plus W2, and if I can get a good approximation factor with W2, the same guy is a factor 2 approximation with W1, then it's a factor 2 approximation with respect to the weight W. So the algorithm which we try to do, we arbitrarily picked up an edge, right? Arbitrary pick an edge E with weight of W is greater than 0, so positive weight. And what did we do? So we basically, the operation which we wanted to do was to reduce weights from all edges incident to E, right? To reduce weight from all edges incident to E. And by how much? By WE. And how did we achieve this in terms of weight factor? So we defined weight W1 of, say, F equal to, what did we say? If F is not incident to E, then if F is not, it is weight of F, right? Otherwise, what did we define? We defined weight of E otherwise, right? So if it means if it is does not belong to this, then it is this. So for every edge, we have given weight of A. And how did we define W2? W2 was defined as W minus W1, right? So this is how we define our weight function. So notice that what happens here is that if you look at this edge, so the only edge which has weight, it should be 0. Okay? So is 0, so the only edge which has weight in this is these edges, and rest everything has weight 0, right? Weight 0, right? Now, and what are the weights of edges here? The weights of edges here is exactly equal to weight of E, weight of E, weight of E, and so on and so forth. So clearly, what is a maximum weight matching here? It will be the maximum weight matching here has weight. So if M is a max weight matching, weight matching, if M is a max weight matching, if M is a max weight matching here, look, graph remains the same, it's just the weight function which I changed. With respect to W1, what is this? Right? The max weight matching can have only weight 2 times WE. Right? I pick an edge incident to this and pick an edge incident to this. Right? That's it. I don't care, I mean, maximal, because all other has weight 0. Right? So, but I can just pick this edge for sure. Right? So, I also have a lower bound. Right? So, any maximum weight matching, so what is the guarantee of weight of M? Is at least weight of M, at most 2 times weight of E. Right? Because every other edge has weight 0. So I do not care. So any max weight matching here is this. So it's a factor 2. If I return this edge, it's a factor 2 approximation to the max weight matching. Right? Now notice what is happening here. Now in W2, right? Like, so what happened in W2? Number of edges that has weight less than or equal to 0, number of edges. So now if I look at the graph G comma W2, because recursively I have to find a solution here, find a solution there. But what happened to number of edges that has weight at most 0 here? Right? That reduces. Right? Because what you are going to do, look at here, it's W minus W1. So clearly, at least for weight E, you would have made this edge 0 because it was a positive weight. And this is what you do, keep doing all the time. So all the time, either once an edge becomes 0 or negative, it remains negative all the time. So at least in every iteration, you are ensured that there is number of edges with weight less than or equal to 0, thank you, is increases. So now you can apply induction on this. Okay? So if you had a factor 2 approximation here, you will get a factor 2 approximation with respect to weight W. So if I have a matching M here, say M W2. So you returned me recursively a matching of weight MW2. At the end, you just return any edge of minimum weight, which is like, or at the end, what will happen? All the edges has weight less than or equal to 0. So just return the weight, return an edge with the maximum weight, which is very easy because everything is negative. So adding any extra edge can only decrease the weight. It cannot increase the weight. Right? Okay. So the base case is perfectly fine. That is 2 times this. But given MW2, I can always assume that MW2 contains an edge. So let's call this edges N, right? Contains an edge from N. Why? If it doesn't contain any edge from N, then I can add WE. It still has the same weight because, because the weight E will have weight. So suppose it doesn't contain, then I will add this edge when I'm considering for W. Okay? I will add this weight. So clearly, by adding this edge in MW2, I would have, what I would have done? Okay, no, we are talking about MW2, right? MW2 is in this graph. So this edge has weight 0, right? This edge has a weight 0. So if I add edge E to MW2, I will not increase the weight, I will not decrease the weight, and hence still remains a factor 2 approximation with respect to weight W2, right? Same set of guys, it still remains a matching with respect to my weight W1, and since you have contained at least one edge here, right, at least one edge here corresponding to this, this is also a factor 2 approximation because you would have decreased all these guys by just weight at most E, right, and you at least know. So this is the algorithm this is a sequential algorithm which we try to implement when the edges are coming in the stream, right? So now notice that, so basically what happens, here I pick up an edge and I decrease its contribution immediately. But I do not know that when I'm applying this operation at this edge at this point of time, whether an edge will come in future or not. So I record this information that, hey, whenever up until now, I will record some information on U and V and will say, hey, this is the set of decrement which has happened at edges incident to U. And so when any edge comes in the future, right? When any edge comes in the future, I will take this potential and remove from this, which will be like, okay, I have decreased all the edges which have been incident on this edges up until now. Okay? So this is the algorithm which we try to maintain. Okay. So I'm not going too much into details, but our weighted maximum matching algorithm was very simple. Okay? It just tried to implement this. Okay, so what did the algorithm do? If you recall correctly, H is phi in the beginning. So this is a set of edges which we are going to sample. Okay? And I had a potential phi v which initialized to 0 for all v in v. Okay? And now whenever a new edge came, for each edge u comma v, what did we do? So we said, okay, fine. And suppose this is a sequence of edges comes. What did we do? We checked if weight of E, okay, if weight of, so say this is EI actually, if weight of EI is greater than equal to, we had some term, but forget for now, phi u plus phi v, right? Then what did we do? Then we said, oh, this is an edge which is good to go for updation. Why? Because what does phi u is storing? If you notice what phi u will store. Phi u, so let me tell you how are we going to update phi u, and then that will be clear. So phi u is going to be weight, phi u plus weight of EI minus phi u minus phi v, right? So look at the edge weight, right? Every iteration, if an edge incident to this, I perform my operation, then I decrease its weight by this edge. And this is exactly what is stored at phi u, and this is exactly what is stored at phi v, right? So when phi u becomes this, and what is the change in EI? So what is the current residual weight of edge EI? It is all the edges which I have dropped, and what is and because phi u plus phi v is phi, the current weight, this weight is greater than this number, I know this is positive, and that is why I am doing this operation at this point of time. Okay? So similarly, we will update phi v and phi v plus weight of EI minus phi of u minus phi of v, right? So if weight of this is more than this, okay, then what we did first, we added e to this, okay? This is all that we did, okay? And then what we did, finally, like if we do not care about, like just for the analysis, it was important that we did things in a way, but now all I could say that return the max weight matching of H, right? And that I know how to compute in polynomial time. So I can, so from this subsampled edges, I can run my algorithm which can actually find max weight matching, but this is not what we will do. We'll say construct a greedy matching M, construct a greedy matching in H by considering edges. So how were we making this? We were going to the base case, we returned something, then we returned something, then we returned something, and then we returned something. So this is, and how we'll realize this? Construct a greedy matching in H by considering edges in the reverse order. They were added. In the reverse order, they were added. This is what we did. So this was the whole algorithm. And what did we analyze? This was a factor 2 approximation. And how did we go about analyzing this as a factor 2 approximation? So what we said is something very nice. Okay. So let M star be the max weight matching. Okay. Notice I cannot give you any upper bound on size of H at this point of time because I have no clue at this point of time. But but we can give such a bound little bit later with hard work. Okay. So what did we define? Okay. So M star be the max weight matching. This is like now we are just doing analysis. And let M be the matching returned by the algorithm. Matching returned by the algorithm. Okay, M be the matching returned by the algorithm. And then we defined something, and what did we call MI as EI plus 1 dot EM, right? So MI is the edge from between the last EI to EM stream because we are doing reverse induction, right? And then we defined a new edge weights. Defined new edge weights. And what was the defined? So these edge weights are going to be like this W2. I mean, I need to come up with something which is very closer to W2. And how did we define? Wi of any E, right, was weight of E minus phi I of U minus phi I of V, where E equal to U comma V. Okay? Now, but what is phi I? I didn't define. So phi I of some vertex is the value of phi before the edge EI was added, right? So just before EI was added, so think of this way. So we have adding edge E1 to EI minus 1, right? At this stage, whatever the value of phi is, we are going to call that phi I. Okay? So this is what is a phi at ith round is phi I, basically this. Okay, right? So two things happens at this point of time, right? When this edge EI comes, either it is added or it is not added. If it is not added, then what happens? If it is not added, because this happens, this is why it is, this is less than this. This is why it is not added, which means this is less than equal to this. So it means this edge has weight either 0 or negative. Right? In my residual graph, look, at this point of time, this edge has weight, because we are going to subtract this edge weight is 0, or look at this WE minus this, right? Why are you not going to add this edge? Because this happens at ith stage. It means this guy has already weight 0. So you never consider this, because anyway in your algorithm, you are only at every time you choose an edge with positive weight, not negative weight. And since it can only decrease the value throughout the process, at the end, every edge which is not inserted in H has weight negative. It is important to point. Okay? Which is the remaining weight at the end, right? Residual weight, right? So so like weight in W2, right? So from W2 we will construct another W2, W3 in W3. So at the end, when no more positive edges are weight, so some guy which became negative or zero weight at some point in time, it remains negative weight throughout the process. This is important to note. Okay? So this is one observation, because the reason why I'm repeating this is just because this is an important algorithm which you should know. And secondly, maybe it was not clear last time, why in Wm, the last weight Wm, why all the edge has weight negative, okay, which I will tell. Now, notice, we were saying, so notice if Ei is not added, then what did we say? Well, then weight of I plus 1 is same as weight of I. Like if you did not add this edge, no phi was added. So weight at I plus 1 stage is same as weight I. Right? But suppose you added, then what changes will you do? Notice what changes will you do. Okay. So suppose Ei was added to H. Okay? Suppose Ei was added to H. Then what happens? Look at weight of E. There could be one thing that here is my E and here are my edges incident to this. This is my Ei. Okay? And here are edges incident to it, and there are edges which are not incident to Ei. Right? So this is going to be weight of I is F if F is not incident to Ei. Nothing will change because their phi u values have not changed. But look at an edge here, okay, which is an incident to Ei. What happens? Like just one incident, right? Okay. If F is incident to Ei, but not Ei, then what will I do at this point of time? From the weight of this edge, I'm going to decrease the weight of Ei, the residual weight of Ei. This is what I do, right? This is what I will do. I will remove it. So what is this? This is nothing but weight of I, weight of F at ith stage minus weight of I at weight of I of Ei, right? This is his current weight, which I'm going to decrease from here. That's it. And for F equal to Ei, I'm going to drop weight from here as well as from here. So this will become Wi Ei, or no, sorry, weight of Ei minus 2 times Wi Ei. Right? Because you are going to decrease his contribution from U as well as from V. Okay? Okay. So what happens? Notice, the moment an edge is added to H, after that step, okay, after that step, the weight of that edge becomes negative. When an edge is added to H, because what are you decreasing from? This was more than his residual weight, right? And look, why did you add? Because it was more than his residual weight, right? And you're decreasing twice of that from the current residual weight. So it becomes negative, right? So at the end, when all the edges has been added, look at Wm. The only edge possibly which has a positive weight is Em, right? Then the only edge possibly that has positive weight is Em, right? So what does that mean? That's the only edge, right? So at that point of time, my algorithm could return look at this. What does it return? So by induction, I wanted to show, by induction, what we tried to show last time? We tried to say, okay, look at the weight I of M star is less than equal to twice weight I of Mi. This is what we wanted to show. And if we were able to show this for all I, we are done. Because what is W1? Is same as weight, because phi u's are 0 at that beginning. So Wi of every edge is this. And what is our base case? Was M. And base case, only edge which is there is this. So M star, whatever, if M star picks Ei or Mi picks Em, that's perfectly fine, right? So what will this guy output if it is a positive weight? So it will output my greedly. I'm doing greedly. It will output me a edge with the maximum weight at this point of time, whatever it is, right? That cannot be less than this. Because for single edge, look at M star. Everything is 0 except maybe this edge, which is common in both, which is Em. Rest is negative. And I have just outputted 1. So if you sum them, it is worse than this number, right? So this is a factor 2 approximation. And then we see how inductive hypothesis happen and so on and so forth. And this is the algorithm which we showed. But this algorithm did not imply any bound on us. So what did we do? We said, okay, let's put some small epsilon. And we assumed another thing after that is that weights of our edges are 1 to poly n. Okay? Weight of E belongs to 1 to poly n. Now notice, if I fix some 1 plus epsilon, right? In the beginning, every edge for the first time when a phi u is like after 0 it becomes something, it becomes at least 1. Right? And after every time it increases by 1 plus epsilon. Right? So it cannot, like if the moment the edge weight becomes more than poly n times, it will never be added. So the number of so phi u changes at most log 1 plus epsilon times poly n. This is the number of times anything will change. So the number of edges which we will have in our algorithm is n poly log n. So number of bits which will be. But our analysis was only for the case when weight of Ei is at least this. And how did we translate this into this? We said, great, no problem. What will we do? We redefine the weight of edges. We said, hey, let's do this trick. Weight of E prime was weight of E, but it was, we reduced this weight by 1 plus epsilon if weight of E was more than phi u plus phi v and less than equal to 1 plus epsilon times phi u plus phi v. Now notice, whenever an edge comes, right, picking an edge, picking w prime E. So now the moment edge comes, I look at its weight, I divide this and then I check, is w prime E greater than equal to phi u plus phi v, right? And if this is true, then I insert this, which is same as, when will this true? This is same as weight of E is at least 1 plus epsilon times phi of u plus phi of v. Right? And then we did our analysis to show that weight of matching that we will return is at least weight of matching m star times 2 times 1 plus epsilon. And that's it. So this is our algorithm from the last time. Okay. So notice, first of all, this is only in insertion mode, and there's no deletion. Okay. And so people have moved from, so this is the most latest result in this direction. We do not, so this is like, as I told you, this is from SODA 17. And as far as I checked the literature, this is the best yet. We do not know how to break factor 2 approximation in semi-streaming model, even when, in semi-streaming model, even in just insertion mode. Okay. But for special classes of graphs like planar graphs and this and that, we have some achievement, like, but not really. So people started to say, forget about giving me a matching. Can you give me an estimate on matching number? Can we do that efficiently? Do you get my question? Like, I'm not interested in that you give me the matching. I'm interested in knowing whether matching is like 55. So you give me this number and I'm perfectly high. So people move from finding matching to estimating matching. Okay? And that will be our topic for some time. What? Is W E by 1 plus epsilon if weight of E is between these two parameters. Otherwise, I leave it weight of E, right? So when you are running this, why are you running this? Look, I have divided by 1 plus epsilon, right? So only time this can be more than weight, W prime of this can be more than this, if your weight is strictly more than 1 plus epsilon times phi u plus phi v. Otherwise, weight of prime I have divided, so it can only become smaller. Okay. So now I'm going to move from, so this is a very simple algorithm. This is nothing much. You maintain certain potentials, and this is basically a local ratio algorithm. And to my surprise, very few algorithm has used local search in streaming. So it's a good model to, like, good way to maybe attack some other problems too. Okay. So now I want to move from, for now, finding matching to estimating matching. Matching to estimating matching. Okay. But to do that, let me first just move and let me ask the following puzzle. I have A1, A2, AN coming in stream. Okay. I want to pick AI. Want to pick AI uniformly at random. Okay. Which means I want to choose some S, which will be equal to some AI. So the probability S equal to AI is 1 over n. So but look, it is very easy if I knew there are n numbers, right? Then I can throw log n bits, whichever index comes, I can keep that. But I don't know, I don't have any estimate on n for now. All I see is my current AI. How are you going to do uniformly, like uniform random sample? Do you get the question? Right? So I have absolutely no upper bound on this. If I had, then there are ways to do this. But if I do not have, how do I do this? And this is one of the basic primitive, like L0 sampling, which is used in graph streaming, or for that matter, any kind of streaming algorithm. And you can do it in order log n space. And of course, you can store all and then do random sampling, but no. You can do it in order log instances. Hmm. There's no vertex. There's some. Think of these numbers, 1 to n or something numbers. Can you be a bit more specific? Like, I'm not able to understand. In a stream, okay, and you have to, you are maintaining a count, like you have some memory record, some, if you want, order log in space, and you will output me a number at the end of the process.
At the end of the process,
Says you will output me a number.
it should be 1 of the AI probability.
It is 1 over n. In fact, what you will be able to maintain is that what you are storing is, suppose up to ith number, whatever you are storing, you can actually prove that this is, you are like from up to this much, it is with probability 1 over I. Yes, you can maintain this, but that's like, let's not get there because then we'll confuse ourselves. Imagine that at the end, you have to give me an element with probability, like you have to return me this and show me that the probability that this is, this, you have given me this with probability 1 over n. You don't know. This is exactly my point. This is what I told in the beginning. You don't know. No, you don't know. If I know, then I can have a counter. Like I can just do log in random bits, and whatever number comes, I just keep this and forget everything else. Only hint is, remember main cut algorithm of Kargar. Okay. So we maintain one memory location. Okay, let's call this S, which is storing something. When the ith guy comes, AI, I replace S with AI with probability 1 over I. That's it. That's the end of the process. This is it. So, like first comes, like you just put it inside that location because it has to be probability 1. So you put it inside. So 1 by I, probability 1 over I. But now I should show to you that we do achieve this. Right? Okay. So suppose at the end of this process, S stores some AI. Okay? So probability that S equal to AI, I don't know, this is like I is some fixed I. So what is the first thing? First thing is AI should go inside this box, and that should happen with probability how much? 1 over I. Okay. And it shouldn't be replaced by anyone else later. And that happens with probability 1 minus I plus 1, 1 minus 1 by I plus 2, so forth, 1 minus 1 over n. Agree? This is exactly what it is. Okay, let's 1 over I times, this is nothing but, if you notice, it is I by I plus 1. Right? Next term is nothing but I plus 1 times I plus 2. And this is nothing but n minus 1 by n. Right? So everybody will get cancel because it's telescopic series, and what you get is 1 over n. Okay? So, this is it. Right? Okay. Excellent. Good. So, if I have to sample one object, then I can do this. But suppose I have to sample k things, not one things, but sample k things. What will go? Like, so, okay, this is good for one thing. Like, okay, so this is, so everywhere I read k things and then you get confused, but when you look at this, this is exactly what is happening, which is very nice. Okay. 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 So now we would like to maintain k thing. Like, I would like to pick, so there are two ways, okay. Select a random subset of size k with replacement, this is one thing, and sample a random subset of size k without replacement. Which one is easy? Like, which one you can just implement this in k in parallel? And when I say in parallel, like you have k locations and you are just doing the same operation at each of these things with replacement, right? If I have to do like with replacement, then I will maintain not 1, S1, S2, Sk, and when each I comes, I go to every memory location and I replace this with 1 over I. That's it, right? So now it's with replacement because same guy could come to several places. So you can prove for yourself that if I run this algorithm in parallel, and this is what I'm, whenever I say in parallel means you are doing the same process independently k times, right? This is what means in parallel. So whenever in streaming algorithm you see some things is done in parallel, basically you are maintaining k different objects and you are doing the same set of operation each time to these set of objects. This is all that it means. Okay? Good. Okay. But what about this? And look, this is with probability 1 over n, 1 over n, 1 over n, 1 over n. So this is completely correct, 1 over n to the power k. But now I do not want this. So how will we go about it? So because then I can start using, let's pick an edge uniformly at random, and you will believe me that I can pick this edge uniformly at random with just order log n bits, right? And even when I do not know the number of edges, I can do this uniformly at random, right? So this is why I am trying to tease this, because I would like to use this terminology, pick an edge uniformly at random. So we are just opening every black box. And so now if I say let's pick k edges uniformly at random, so now when you are going to pick k edges uniformly at random, more likely I would like to pick without replacement. So how do we achieve that? Right? So first let's have n numbers coming in sequence, and I want to pick k numbers from here. Okay? So as always, you will maintain, yes, with what probability? You're correct. This is what we will do. Yeah, but so what we actually it's clean algorithm. It's not something very. So I maintain k location. Okay. So for I equal to 1 to k, assign ai to si. So I do nothing. For first k, this is exactly the way I was trying to do. Okay. Now for I more than k, okay, okay. pick a number from 1 to I uniformly at random. This we can do, right? Like I can pick, so when ai'th element comes, I can pick a number 1 to I uniformly at random. No, I want to do 1 to I, okay? Pick a number, say S star from 1 to I uniformly at random. If S star is less than equal to k, if S star is replaced less than equal to, if S star is replaced, then replace S star with AI. Otherwise, you don't. So this is it. This is the end of the process, right? So when I'm at jth element, basically I generate a number, right, from 1 to that number, and if that number happens to be between 1 to k, I look at that particular index and delete that element and put myself there. This is what I do. Okay, good. So let's do the probability computation. So what I'm going to do, okay, so rather than showing, so I would like to show what? Probability that a fixed set Q of size k is in my locations is equal to 1 over n choose k. This is my goal, but I will not show this. Okay, I'm going to show this, and it just follows from there. Probability that some AI belongs to my memory cell is equal to k over n. If I show this, I'm done, right? If some AI belongs to my memory, like AI belongs to my memory cell, this is true for any AI. For all I, probability that AI belong to my memory cell is equal to k over n. If I show this, I'm done, because then I will delete this. Among them, it will be k minus n minus 1. I move this, it will be this, and that is precisely equal to 1 over n choose k. So let's just do this, and we will be happy. Okay. So if it is in the first k index, it is with k over k. If your number of, if AI belongs to first k index, then I have actually assigned them there, right? So the problem comes when later, okay? So probability that AI belongs to my location is what? First of all, right? No, first of all, notice that at any point of time, this contains distinct elements. This is very clear, because you delete it. So basically, if you go at some location into this, you should never be removed. Be thrown out from the elements coming later. Right? So what is the probability that AI is in my location? Okay? This is equal to, look, so out of I, how many numbers are good for me? K minus I numbers are good. K numbers are good for me, right? Which is k over I. Because what I'm doing, I'm generating a number from 1 to I uniformly at random, out of which k places are good for me. Okay? Now, what do I want from other people? Not to touch my location. From the I plus 1th onwards, that guy shouldn't generate the index of me. Okay? So suppose that location is X, where I replaced AI. Now, what is the probability that you hit this location? Is 1 over I plus 1, or right? So what is the probability that you don't hit this location? Is 1 minus 1 by, so this is 1 minus 1 by I plus 1, right? And then it is 1 minus 1 by I plus 2, 1 minus 1 over n. So if I forget this and I write down this, what will I get? I will get cancelled. This is exactly the same formula, but now you will get k over n. Right? Because everything else will get cancelled, k and n will survive. Right? So we have shown that every element goes into my memory location with probability k over n. Any element has an equal chance of going over there. So now it has gone. What is, so if you remove this, now you can do induction or something, right? Okay. And so this word is called reservoir sampling. So if you want to know more about this, this is called reservoir sampling. Okay? Okay. So this is the basic tool which we will be keep using it from now onwards. Okay? Any question? Okay. So now what we will try to do, we'll go back to matching on graphs of bounded arboricity. Okay. Okay. So now we are going to estimate matching, in graphs of bounded arboricity. So what is a graph of bounded arboricity? Okay. So definition. I mean, this is, I don't know whether this is a definition, but this is fine. Actually, this is a graph has arboricity alpha if for any subset, of any subset U of Vg, okay, edge induced in a graph is at most alpha times u. This is my definition. Okay? What is an arboricity of planar graph? What is an arboricity of planar graph? Yeah. 3. Right. So the theorem which we'll like to prove, and this is, so the theorem which we want to prove, suppose G has arboricity alpha, then there exists order epsilon inverse polylog log Cn, okay, space algorithm that like in insert only model, that approximates the size of maximum matching, size of the largest matching. We will not do weighted because it's a bit more tricky. The largest matching, size of the largest matching up to factor two plus alpha plus epsilon. Okay? But look at the space usage. It's just like polylog space. Literally, it's a poly. It gives you like, even for planar curves, like a factor 5 approximation to some extent. But this gives you in polylog space an estimate. Okay? Okay. Now, what to keep track of in streaming algorithm? What to keep track of? Suppose if I gave you bounded degree graph, what will you try to do to keep an estimate? If I gave you a graph of degree 3, can you do this in log n time? Estimate? Suppose if I give you a connected graph, and I gave you the graph is connected and it's a degree at most 3. What should I do? And it's only insert only. I just count the number of edges and return that to you. That's a good approximation to maximum matching. Clearly, it is greater than maximum matching, but it is not more than some 4 or 5 times maximum matching. Do you know why? Why? Do you know this fact? What is Bayes' theorem? What is Bayes' theorem? You are coloring edges so that no two edge adjacent gets the same color. Okay? And what does this say? Every graph G is delta plus 1 edge colorable. In fact, every bipartite graph is delta edge colorable, right? But every graph G is delta plus 1 edge colorable, right? So if delta is 3, maximum degree delta is 3, then what you know? Each of the colored classes is a matching. Each of these color classes is matching, right? So if I return number of edges, I have given a factor 4 approximation to those. Agreed? It's like, of course, you can argue in lots of ways, but this is the most tight analysis we could hope for, right? So every graph G is delta plus 1 edge colorable. And what is the meaning of edge colorability? No two edges adjacent have same color. So if I look at any colored class, it forms a matching, right? So maximum matching can only be more than one of the color class size, right? So if I can color into 4 parts, then if I returned you total number of edges, I definitely told you 4 edge colorable graph. Now, this is what I would like to use, but it's a graph, it's not a graph of bounded degree, right? That such a simple estimate will work. And look, there is a long line of work here. It's not what I'm giving you an algorithm is the most refined and the best one, but there's a long line of ASA, SODA, prox, and then this. So it's a long line of research has happened on this too. Like I'm not giving you the literature because it's a class. Okay. So first thing is, what is like in graphs of bounded arboricity, to be able to find an object A which gives a good estimate, and B, somehow we are able to find a good estimate for that, right? Number of edges in graphs of bounded arboricity is not a good parameter. I cannot say that if I just return the number of edges, it is a good algorithm, or is it a good algorithm? So, or I could also have thought about this, like that this is exactly what I'm saying. So can be guaranteed. Look, for bounded degree, this theorem guarantees you that there is a matching of size m over 4. In some sense, this is what it guarantees, that there exists and matching of size, max matching is at least m over 4. So this is a good approximation if I tell you this number. So could you, like orientation, anything, that's perfectly fine. But could you give me some lower bounds on graphs of bounded arboricity, or there is no such lower bound? Take a click on the size n, subdivide every edge, okay? Subdivide every edge. The maximum matching here is the original vertices, right? Which is like root n compared to the number of vertices. So in graphs of bounded arboricity, my matching could be way more smaller, like in terms of n, compared to the number of vertices in my graph. And since the graphs of bounded arboricity, number of edges is some alpha times n. So if we are happy to use alpha as my approximation ratio, if I could have been able to prove to you that the number of edges provides a good this thing, then I would have been happy. But here's an example. Take a click, subdivide every vertex. I claim this graph has arboricity 2 or some constant, right? At least its degeneracy is 2, and they're right. But I cannot have matching more than m, because every degree 2 vertices is an independent set. So if you have an independent set, and this, the maximum matching is upper bounded by this, right? That can only minimize, because once you use this, you cannot use this, right? Because these are independent sets, the only way for them to be matched is this. So I mean, in some sense, this provides you, and this is like root n. So this is not a good estimate, because the number of vertices is n square, because you took a click and subdivided every word. Independent set is n square, right? So this is n square and this is n. Not n square actually, n choose 2, because you have click. N.
Oh, that's n.
But with respect to n square 2, it's like it has nothing to do with the number of vertices, and hence it has nothing to do with number of edges. So that I cannot use as an estimate. So I need to find some other set of parameters which gives me this good bound, and also we should be able to estimate good in the stream. That's all. Okay? So, okay, I mean, why people come up with this object, you will see in a minute. Like, but I guess okay. Okay. Okay, so I'm going to define a notion which is called a good edge. An edge UV is good, okay, is good. So now UV is an edge, so it is going to appear in some stream, right? If the number of edges incident to U or V after UV in the stream is upper bounded by alpha. Okay? So my streams are coming. Here comes UV. I am not interested in my stream before how many edges. But after this, I look at the edges which could this or this. Number of edges that appears after UV in the stream, in the remaining stream, should be bounded by alpha. Then I am going to call this edge good. Okay? So if you, in some sense, it is like are both at most alpha. Okay? So this is like, I do not know this degeneracy ordering or alpha ordering, but somehow I am trying to mimic that in my head and try to see what happens. Okay? Now, first of all, if we are able to count good edges, A, why does it provide a good estimate? That's the first question. And secondly, how do we count good edges nicely in the stream? So one is a graph theory result, that structural result, and another is just a like algorithmic result. How do we maintain the estimate on good edges? Okay. So in the remaining 15 minutes, let's do the graph theory part and come back and let's do the algorithm part. Okay. So what I would like to prove. Okay, I have a lot of time, so it's fine. Okay. Okay. So this should be enough. So the lemma or theorem which I want to prove is let G be the number of good edges. Okay? Let G be the number of good edges. Then G is at least match of G. So that's a lower bound, which is not obvious. And this is alpha plus 2 or alpha plus 1, it should be alpha plus 2, alpha plus 2, yes. Match of G. So if I can get a good estimate, then I will get alpha plus 2 times something. And what will algorithm do? Algorithm will give you an estimate on G, like some, I'll give you a number n hat, which will be like 1 minus epsilon times G, 1 plus epsilon times G. So I will use this 1 plus epsilon G and multiply with alpha plus 2 and get my desired algorithm, of course. Everything is randomized. There's nothing deterministic, right? We will use this, the sampling procedures and all this, but in a very subtle way. Okay? So this is what will be the goal. But first now let's concentrate on this graph theory result. Okay. So let's look at a graph G good. So how do? I add the vertex set. Okay? The vertex set is same. And whenever edge comes, why it is good? Because there are at most alpha edges incident to him. So you add all good edges here, just good edges. What is the maximum degree here? What is the maximum degree of any vertex? Huh? Or alpha plus 1? I claim that this is less than or equal to alpha plus 1. Let's prove this. Because if we prove this, we are done. At least with this bound. Why? I apply this lemma, Weijing's theorem, right? So, alpha plus 1, so there exists a matching, so there exists a edge coloring of size alpha plus 2, right? So, maximum matching of this graph. So, basically we will, if I show this, then I will be able to show that G is less than or equal to alpha plus 2 times G, no, alpha time plus 2 times maximum matching of G good, right? This I can show, which is less than or equal to alpha plus 2. This is a subgraph of my graph. So, maximum matching in G can only be larger than my subgraph, right? So, into maximum matching of G. So, if I show this bound, then using Weijing's theorem, we will be done with the upper bound. Okay, let's see. Okay. Now look at a vertex V, right? All the edges which are incident to him are good edges. So, look at yeah, first edge in the stream, incident on V, right? Look at the first edge from here which is incident on V. What does it tells us? That after this, there are only alpha guys, because this is good guy, right? So, only after this at most alpha edges on V are incident, which are good. That's it. Right? So, this edge plus this, which is alpha plus 1. That's it. There's nothing more to it.
The alpha edges may not even be good, but
that's good. That's upper bound, right? Yeah. Agreed? So, just look at the first edge. That itself tells you on V, after me, only alpha edges are incident. And this is true about every vertex. And that's it. Okay? So, is the, okay. So the hard part is showing the lower bound, not the upper bound. Okay? So, and this proof is given in Sosa 2018 paper. So, before it is proved using some fractional matching, some polytope and blah, but someone gave very cute 2-line proof, both lower and upper bound, which, but otherwise it's a like 8-9 page proof with even worse constant in some other papers, like some 7-8 pages. Okay? So, what I'm giving you is like Sosa paper, okay, which was also easy for me to read. So, that's easy. Okay? So, we are done with the lower bound, upper bound. Okay? So, all we have to show is the lower bound, and that's a bit tricky, rather not tricky, but okay. Let's call H heavy vertices. And what is the property of heavy vertex? for every u in H, degree of u is alpha plus 1. And this is the remaining vertices. Okay? Okay. Now I'm going to define a term called LU. What is LU? It is set of last alpha plus 1 edges incident to u in the stream. Incident to u in the stream. Okay, so this is what it is. LU is a set of last alpha plus 1 edges incident to u in the stream. Huh? U is a vertex. No, like in general. This is the definition. We'll come to H. Okay, we'll come to H. Okay, so but let's LU is this my definition. Okay, notice. So they had a small claim. Observation. UV is in LU intersection LV if and only if UV is good. And H is good if, so this is very simple. So if U and V belongs to this, look at U and V. After this, how many edges incident to V are there? At most alpha, right? Yeah, because LU is the last edge incident to U, right? In which UV is there. Then after that, there are at most alpha edges incident to U. Similarly, with respect to V, so UV is good. Because LU itself contains alpha plus 1 edges, and this edge is present in both. Okay. Other way around. If it is good, if this edge is good, then look at V. How many edges are incident to him after this? At most alpha, maybe less. So if in the stream, I look at last alpha plus 1 edges, definitely I will pick UV, right? So this is good. Okay. Say an edge UV is wasted if U comma V is in LU union LV minus LU intersection LV. Then I will call this edge is wasted. So basically it's, look at all the edges here, these are wasted edges. Okay. Now let's come to H. So W, X, Y, Z. X, Y, Z. So what is W? Is number of good edges with no endpoints, number of good edges with no endpoints in H. Okay? So these are good edges which are completely contained here. Right? X is number of good edges with one endpoint in H. So this will be these edges, right? But there could be more edges, okay? There could be more edges. But so this yellow color edges is W, this is X, and what is Y? Number of edges, number of good edges with both endpoints in H. Okay, so there will be this is Z, and what is this is Y, and what is Z? Number of wasted edges with both endpoints in H. Okay? Let's count I want to count this LU. So look at, so it definitely, because he belongs to alpha, everybody has alpha plus 1 edges. So each LU has size exactly alpha plus 1, because every vertex belongs to H. Its degree is at least alpha plus 1. So I mean, if you otherwise, so each LU, right, this is, so first of all, this is equal to alpha plus 1 times mod H. This is very clear because each, but what else is this? Okay, let's try to understand this. Okay, so look at any edge in LU for U in H. Either it is a good edge with one endpoint here. Look at fix LU in H. Fix LU in H. Some alpha plus 1 edges. Some alpha plus 1 edges. Let's classify them. Oh, you are a good edge with one endpoint. Oh, you are a good edge with both endpoint. Or you are a wasted edge. Yes? What is, there's no set Y. Why not? It's in the stream. It's in the stream. What did I define? I said an edge is good if after me in the stream. Right? So, for example, look at any vertex here, look at the last edge incident to him. I mean, maybe after that there is nothing else after that. Right? And like last edge of the stream, which is incident to this, that's a good edge because there's nothing after him. Okay? So it's not a static definition, it is on the stream. Okay? But now look at any edge here. Okay? It is good with both endpoint, good with one endpoint, or wasted. Okay. Good with both endpoint is going to contribute to two sets. Right? If you fix a set U and V here, or say A and B edge. Now this edge is good, right? So it is good means after AB there are no more than alpha edges incident to B as well as A. So LA is going to contain this edge, LB is also going to contain this edge. Then we are going to count this edge twice. So how many edges were here? Y edges. So this is definitely contributes to Y. Now plus something more. But look at all the edges which are good with just one endpoint. It is in only one of them. And how many of them were there? X of them were there. So there are X of them. Now let's look at number of wasted edges with both endpoints in edge. What is a wasted edge? I told you, right? Wasted edge means look at U and look at V, right? He is either here or here with respect to some LU. But notice he can only be in one of the sets here. It cannot be that in one set it is here and other set he is in the intersection. Right? Because then I would have taken the intersection of those two things and that edge would have been good. That would not have been a wasted. It means you have to add W to it because it occurs exactly once. So what did we get? 2y plus x plus w is equal to this number. No. Number of wasted edges with both endpoints in edge. Oh, sorry. This is my mistake. It's Z. Okay, that is mistake. Okay. So we have got one upper bound on H. Okay? Okay. Can I get a lower bound on Z plus Y? There's a lower bound on, there's an upper bound on Z plus Y, if you notice. What is an upper bound on Z plus Y? Upper bound on Z plus Y is less than equal to, what is a, it's a graph of bounded arboricity. It's alpha times mod H. Okay. Agree? This is all it is. Okay. So I want an upper bound on x plus y.
So when that
Edges here.
yes, but there's no overcounting, they're disjoint sets.
They are disjoint set because you are good or wasted. You can't be both. So I can write x plus y plus y plus z equal to alpha plus 1 times mod s. So I can get x plus y is equal to alpha plus 1 times mod h minus z plus y from here. So what is x plus y? Look, or this is, yeah, this should be less than or equal to or greater than equal to, greater than equal to, less than equal, no, greater than equal to, right? Because if we are removing upper bound, right? So this is alpha plus 1 times mod h minus alpha times mod h, which is greater than equal to mod h. So we have a bound here. Now we should be very close. Now I think why it is saying this. is it true that every edge here is good?
That's what I thought, because
Yeah, this is true because look at every vertex here. Degree is at most alpha. So every edge here is good. Right? Every edge here is good because its degree is at most alpha. Because these are degree of vertices of alpha plus 1. All these vertices are degree at most alpha. Okay? So what does it mean? So now, okay, so let me, so we are done now on the bound. Okay? So now let EL be the set of edge with no endpoints in edge. So what is EL? Is equal to W. Because every edge here is good. So every edge here is good. No. EL is be the set of edges with no endpoints. And we just observed every edge here is good. So EL is equal to W. Because that is how we define this. Now, what do we know about this? Okay. So now let's look at EL plus x plus y is at least how much? W. But what is EL plus x plus y? Is G. EL plus x plus y is basically G. Now, this is this is equal to EL plus mod H. Agreed? What is the maximum matching that you can hope for in this graph? I claim that this number is at least maximum matching of G. Look at any maximum matching. Okay? It uses some edge from here. It uses some edge from here. And it uses some edge from here. Right? Look. So look at your maximum matching, no? Look at your maximum matching. Let's delete all those edges which contains vertices of H. How many edges did I delete? At most, mod H. Look, I write down my max, this is my max matching. I delete all the edges which contains any vertex incident to H. I will never remove more than H edges. Where are the remaining matching edges? From here. So clearly this plus this number is greater than any maximum matching of G. Done. Right? Maximum matching can only contain less number of edges, but here I have given you all the edges plus this. Right? So whenever you have such kind of partition, you can always, and if you are able to take all the edges from here, this plus this size always forms a lower bound of the matching size. And it is true about any partitioning. Okay? So this is nothing. So this is what we have shown. Right? So we have given you a lower bound that if we are able to estimate G properly, then we get both lower bound and upper bound. Okay? So and that's the place where let's end. Okay?